Today I thought we'd take a look at DMVPN, Dynamic Multi-Point VPNs. This is a good extension of the tutorial that I did a little while ago on using IPSec over at GRE Tunnel. What you do with a DMVPN is you take that concept and you expand on it. So I've drew up this little network map here that we're looking at to give an idea. Let me explain the basic concept first, and then we'll go through the configuration. So if we had a situation like this where we had our business and we had 5 sites on it and we wanted to do a full mesh connection between the sites and let's say they were all interconnected by the internet. We could set up a GRE tunnel using IPsec. And if we want to do a full mesh, what that would be is a tunnel from router 1, which is going to be our headquarters. We'd have to configure a tunnel from router 1 to go to router 4, and a tunnel from router 1 to go to router 2, and from router 1 to router 3, and router 1 to router 5. And then for a full mesh, we'd want these other sites that are represented by R2, R3, R4, and R5 to also have connections to each other. So we'd have to do another tunnel from R4 to R2, and another tunnel from R4 to R3, and another tunnel from R4 to R5, and so on and so on. So you end up with configuring a lot of IPsec GRE tunnels to make that work. What DMVPN does, in a nutshell, is it automates a lot of that process for you. So again, in this case, we have our data center. You have to think of DMVPN as kind of it's a hub and spoke configuration, kind of mishmashed in with a frame relay style network where you have one hub site. If you were doing a frame relay, that was not a full mesh frame relay. So what you do in a DMVPN configuration is you configure router 1 and you build a tunnel from router 1 to router 2. So you build a tunnel here. And then you build a tunnel from router 1 to router 3, and a tunnel from router 1 to router 4, and a tunnel from router 1 to router 5. Same thing that we have to do manually for a full mesh configuration using IPsec over GRE tunnel. But for all these spokes or all these satellite sites to communicate to each other, the administrator does not have to go in and configure a tunnel from router 4 to router 2, or a tunnel from router 4 to router 3, or from router 4 to router 5. The DMVPN configuration dynamically builds those tunnels as it's needed. So if if there's a network behind router 4 and it needs to talk to something in the network behind router 3 down here, it dynamically builds this tunnel from router 4 to router 3, uses it, waits for it to time out, and then it tears down that tunnel. All that configuration and information is all stored, if we will, on our hub router, in this case our data center. So router 4, we got a network behind router 4, it needs to talk to router 3, it goes down here into its hub site and says, hey, I need to build a tunnel to router 3. Router 3 says, here's your next hop information. Router 4 says, thank you very much. It dynamically builds this tunnel. These two talk to each other. They're done processing data. The tunnel is tore down. The nice thing about DMVPN is that we can run our internal routing protocols across it. Now, the way that this works is very, very much like some frame relay implementations. Let's say we have router 4 here, and we add a new network to router 4 and advertise it into our EIGRP process. Router 4 sends out an update. It does not send the update to router 2, router 3, or router 5. It sends it only to the hub router. So router 4 sends an update to the hub router. The hub router receives it, adds it to the routing table, and sends it back out to the other routers that are in the configuration. So it's an interesting animal. We got some IPsec going on. We got VPN tunnels going on. We've got a throwback to a non-broadcast multi-access type of network infrastructure. We got to turn off some split horizons to make this work. We're going to be setting up some mGRE tunnels, multi-point GRE tunnels. So just like this physical interface connects to everything, we're going to set up a GRE tunnel, one tunnel on each device to connect to everything. It really simplifies the work that you as an administrator have to do when you want to create IPsec tunnels between sites. But there are some things to be aware of and some possible gotchas in the configuration as well. So let's run through this real quick. I'll show you how to do some basic configurations, and then we'll do some show outputs, and I'll show you some of the concerns that I have with DMVPN. Let me also state that I don't know much about DMVPN. I got interested in it, did a little research on it, found some information on Cisco's websites, did a little research, and thought I would mock it up and see what the ins and outs of it are. So after we mock this up, I'll show you some of the things that I found out, some of the things that caused me some concern, and we'll take it from there. Okay, so as I mentioned in our configuration, we're not going to configure 4 spoke sites. We're only going to configure 2. Routers 2 and routers 3. 4 and 5 are going to be exactly the same. And the more spoke sites you have, the more scalable DMVMP it becomes. The less tunnels you as an administrator have to create manually. For our purpose, we're only going to do router 2 and router 3. And router 1 is going to be at our hub site, our data center site, our main site. Each one of these routers has an internet connection. Notice the first 3 octets are the same, but they are each in their own /30 network space. And behind each router, I put a, let's call it a client network. It's a loopback on the router, but we're going to treat this as our client network. Each of these routers is running an EIGRP process number 10, advertising this client network into EIGRP. But right now, they have no connection to each other. So let's hop into router 1 and start that basic configuration on our hub router. Our hub router has the most configuration to it. It's the one that has to tell R2 and R3 and R4 and R5 how to build their tunnels to other sites when they need to. So we have to do a little bit more configuration on our hub router than we do on the spoke routers, but not too much. So let me bring up R1 and we'll get started. Okay, let me pull this into the window. Here's R1, our hub router. So the first thing we're going to do is I want to verify that R1 can actually reach these other routers. So R1's IP address is .1, its default gateway is .2. Router 2's IP address is .5, its gateway is .6. And down here for router 3, its IP is .9, its gateway is .10. So I'm just going to do a quick ping, make sure I can get all those. 54.45, good lord, 45.12.1, which would be itself. 2 is its default gateway. 5 is router 2. 6 is router 2's default gateway through the internet here. 9 is router 3. And 10 is router 3's default gateway on the internet. Okay, so we can ping all that. We're good to proceed. So what we do here for the first steps is the same thing that we went through when we set up a GRE tunnel using IPSec. We have to set up our basic IPSec parameters. So our ISAKMP policy, our ISAKMP key, because we're going to be using a pre-shared key in this example. We have to create our transform set for our IPSec transform set. And then we're going to vary it a little bit from what we have to do. We don't create a crypto map. We don't create an access list to tell it which information to encrypt. So let's get the first few steps done. So we have get our basic IPSec tunnel up and running. So the first thing we need to do is create an ISAKMP policy. So we're going to do ISAKMP policy 10. I'm going to kind of fly through this rather quickly. I did another video about IPSec over GRE where I explained this in a little bit more detail. So if I'm going kind of fast, just pop back over to that video and take a look. So IPSec policy number 10, we're going to use an encryption. AES 192-bit. We are going to use a hash of MD5. Let's set up our authentication. We're going to use a pre-shared key because I don't want to mess with our certificate server. And we're going to put it in Diffie-Hellman group number 2. Alright, so we're done with our ISAKMP policy. Now, because we said we were going to use a pre-shared key for our authentication, we have to define that pre-shared key. So crypto ISAKMP key, and then the name of our key, we're going to call ours ISA key. Now, what do we got to do? There's a 0 we got to put in here. Yeah, 0. And then ISA key address. Now, in the previous video, when we set up our ISAKMP key, you had to specify the host address of the host name or address of the other end of this tunnel that was going to be using this IPSec GRE tunnel. Now, because this is going to be a multi-point tunnel, we can't specify a host. I guess you could specify a list of hosts, but what we actually do here is we say any. So anything, as long as they have this key, they're allowed to initiate an IPSec phase one, an IPSec phase 1 or an ISAKMP configuration. Okay, now let's set up our crypto map, which is our IPSec phase. So we go crypto IPSec this time instead of ISAKMP. We're going to do a transform set. Let's call it DMVPN trans set. We're going to use AES. We'll use, let's say, 256-bit. We're going to use MD5. And boom, that's our transform set. Alright, we're done with our transform set. Now, when creating a point-to-point IPsec tunnel, you normally would create a crypto map, define your interesting traffic with an access list, something like that. What we do in a multi-point GRE that we're going to be using for DMVPN is we create what's called a profile instead. So crypto IPsec profile, we'll give it a name, DMVPN profile. This is just the name of our profile. We're going to set a timeout on this. This is how long that dynamic tunnel waits before it is tore down, before it automatically tears it down. We're going to do it in seconds, and the minimum we can do is 120. So we're going to set it to the minimum, just so I can point out some of the things that I've noticed when messing around with this. So a minimum of 120 seconds, and then we say set transform set to be the name of our transform set, which was right up here. Done. Okay, so we're done with our profile on that one. All right, the next thing we need to do, so that takes care of all of our IPsec stuff. We've done our ISAKMP, which is phase done. We've done our IPsec policy, which is phase 2. We've done a profile, which you can kind of think of as a map, although it really isn't. We do a lot of our map statements actually on the interface. But the profile kind of ties things together. So we're going to create our tunnel interface now. Interface tunnel 0. We give it an IP address. And back here on our map, our network map, I noted for our DMVPN IP plan, router 1, the tunnel interface is going to be 1.1. Router 2 is going to be 1.2, and router 3 is going to be 1.3. So we're going to give this an IP address of 1.1, 192.168.1.1, and they all are in the same network, so a /24. Might help if I put the keyword address in there. All right, we are going to do a no IP redirect. We're going to reduce the MTU size down to, we're going through the internet with encryption on top of the packets. Now we're going to get into something that does the next hop. This is the configuration that when the spoke routers come to the hub routers, it keeps a database that tells them where to go. So if the host behind router 2 need to speak to the host behind router 3, it uses a protocol called NHRP, Next Hop Resiliency Protocol, Next Hop something protocol. Router 2 says to router 1, hey, I need to get to this network. What do I do? Router 1 says, oh, that's easy. Your next hop address is this. Router 2 says, thank you very much. It builds a tunnel between router 2 and router 3 and sends the traffic back and forth. Once 120 seconds have elapsed with no traffic, that tunnel is tore down. Router 2 and router 3 in our instance have no knowledge of how to build this tunnel to each other. They have to go to router 1 to get that tunnel information. So let's drag router 1 back in here, and we're going to configure that part of the IP NHRP authentication, NHRP authentication, and for the authentication we use our ISAKMP key. So up above here we define the ISAKMP key as ISA key, our phase 1 key, our pre-shared key. So there's our ISA key. We'll copy that and paste it down there. IP NHRP multicat map multicast. Now we're building what I had mentioned, which is kind of like a crypto map. It kind of does the same thing, only much more so. Multicast dynamic. What this tells it to do is to allow dynamic multicast protocols to use the dynamic tunnels. And in this case, we're using EIGRP, which is a multicast protocol. So we want to make sure that multicast is allowed. NHRP, we're going to give it a network ID. We're going to call it network ID 1 in case we had more than one of these set up. We are going to turn off split horizon for EIGRP process 10. Now I had mentioned here when we looked at the map, there is only one real interface here. So if router 2 does an update, it sends it to router 1 through FAT00, and then router 1 has to send it back out through that same interface to the other routers. Now in this case we're creating GRE tunnels, but it's still, we don't have to create multiple tunnels. We're creating a multi-point GRE tunnel. So there's going to be one tunnel coming in, and the updates are going to come in through that tunnel, and router 1 has to turn around and send those updates back out through that same tunnel interface to the other routers that are in the DMVPN network. So we got to turn off split horizon, or else that won't work. We also need to turn off next hop self for that same process. Okay, that takes care of the next hop self. Now we need to specify a tunnel source, which is fast 0/0. Tunnel source fast 0/0. And tunnel mode, we're going to tell it that it's going to be a GRE multi-point tunnel. And tunnel, we're going to set up a tunnel key. We'll use 0. And there our tunnel interface comes up. And the last thing we want to do is add our IPSec layer on top of our tunnel interface, or our multi-point tunnel interface as we've configured here. So we're going to say tunnel protection IPSec. It's going to be the profile that we created called DMVPN profile, right? Right here. This guy right here, the profile that we created earlier. So that's the encryption layer that we want put on that mGRE tunnel, multi-point GRE tunnel. Okay, so we're done with our tunnel interface. The last thing we need to do is add the new IP space that we created to our EIGRP process. So right here, 10.1.1.0 is the network that's behind router 1. We need to add this network, our virtual tunnel interface network, to the routing process as well. So we are going to say router EIGRP 10 network 192.168.1.0. So we're adding our GRE tunnel interface IP space to the routing process. Alright, that's all we need to do on router 1. Now, I'm just going to slide this up out of the way because we do need to come back to it. Let's get router 2 quickly. Now, router 2 is our first spoke router, our first spoke site. So what we need to do on router 2, go into config mode, and the first process is the same. We still need to set up all the same IPsec, ISACamp policies, IPsec policies, the profile, password, all that stuff that we did on router 1. We need to recreate on router 2 so we can form the tunnel. So we're back on router 1, show run, and I'm just going to copy and paste all that information from router 1 right onto router 2. So this is all the information we need: our ISACamp policy, our password, our transform set, and our profile. So we're just going to copy that from router 1, flip over to router 2, paste it in there. There, now all of our policies match. Okay, next thing we need to do is create our tunnel face. Now, here's the interesting thing, and let me point this out in case it got missed. We are not creating a tunnel interface from router 1 to router 2 and another tunnel interface from router 1 to router 3. They're both using tunnel 0. So tunnel 0 goes to this one, tunnel 0 goes to router 3. Same thing from router 3, tunnel 0 is going to take it to router 1 when it needs to, and tunnel 0 is also going to take it to router 3 or router 4 or router 5 whenever it needs to. That's why we're using mGRE, multi-point GRE. We can have multi-point configurations over this single interface. Again, very much like a frame relay network. So that's why we're only creating a single tunnel interface on each device. Okay, so we created our tunnel. The next thing we need to do is give it an IP address, 192.168.1.2. Again, looking at our table back here, router 2 is going to get 1.2. So there's its IP address. We're going to do no IP redirects on this one. IP MTU, same MTU. Knock that down a little bit because of the encryption. I don't know if I need to back this out or if it'll... I think it'll just override it, but okay. IP, next hop, resiliency, whatever, protocol, authentication. I think we got, it's going to again be our ISACamp key, which we copied right up here. ISA key goes in there. We want to make sure our dynamic routing protocols can get across it. So again, multicast, IP next, RP. I always forget the map multicast dynamic to allow dynamic multicast routing protocols to use our multi-point GRE tunnel. We are going to say your IP next hop, RP, the next hop server, or the one that can tell you how to form your tunnels, is 192.168.1.1. This is our hub, the tunnel IP address of our hub, right over here. Router 1 gets 1.1. It's our hub. So we're telling router 2, you got to go to the hub to get your information, to get your next hop information. Now we tell it, by the way, to get to 192.168.1.1, you need to use the real IP address on that interface, 12.1. So this is our map. It says to get to 192.168.1.1, you really need to use 54.45.12.1, which is the real IP address of FAST00. So that takes care of that. Then we need to do something very similar to allow the multicast to work. Map multicast, and we're telling it to multicast. You also need to use this external IP address for your multicast, like EIGRP in our case. We got to give it a ID, and we used ones on our core, so we'll use one on our hub. We got to use a tunnel source. Interface is going to be fast 0/0, because that's the only interface that we've got. We're going to use tunnel mode GRE multipoint. Same thing as what we had to do on the hub site. We're going to use tunnel key 0, and we have to add our IPSec, tunnel protection, IPSec policy, tunnel protection, IPSec profile. Having trouble typing. And the name of our profile, which was DMVPN profile. We take that, put it down there. And that's going to add the IPSec layer on top of our mGRE tunnel. We're going to exit out of that. And just like we did on router 1, we have to add that tunnel subnet to our routing process. So router EIGRP 10. Network 192.168.1.0. All right, so that adds the network to our process. And just like that, we see a new neighbor come up. 192.168.1.1. If you remember our diagram, 1.1 is the GRE tunnel IP address that we assigned to router 1. So router 2 that we're configuring now sees router 1 as an EIGRP neighbor. So that's it for router 2. Let's hop on over to router 3 and configure that. Now the nice thing about this, once we have one spoke router configured, the other spoke routers are almost identical. The only thing we change is the IP address that we assign to the tunnel interface. So we can do lots of copying and pasting here. So let's go back to router 2, do a show run. We can grab all of our IPSec information. Right here, our ISACEMP map, our ISACEMP password, our transform set, and our policy. We take all that from router 2 and we can pop it onto router 3. Interface, we're going to create our interface, tunnel 0. Give it an IP address, 192.168.1.3 in the case of router 3. And then I did the same thing again, didn't I? Forgot to use address. And then router 2, we can copy all the other information from the tunnel interface and paste it into the third spoke router. So everything except the IP address, we copy all of this. And put it into tunnel 3. Now we should see our IPsec. There we go. And the last step again is to add in this router's EIGRP process to add our new DMVPN network segment. So router EIGRP 10 network 192.168.1.0. And there we go. We see another neighbor come up from router 3. So router 3 now sees the hub router, router 1, as an EIGRP neighbor. So let's back out of this a little bit. So now that we have our neighbors formed, let's do this. From router 3, let's ping the, well, let's do this first of all. Let's make sure we see everything in our routing table. So show IP route. Okay, so this is router 3. So we see the 10.1.1 network, which came from router 1. We see the 192.17, which came from router 2. And you can see both of these are through EIGRP. If we do show CDP neighbors, show IP EIGRP neighbors, you'll see that it actually only has a neighbor relationship with 1.1, which 1.1 was assigned to our hub router from our VPN tunnel. So it's got a relationship with 1.1. If we do a show crypto ISACEMP SA, you'll see right here we only have a security association back to 12.1, which is our hub router. And if we hop over to router 2, we should see the same thing, only basically in reverse. Show IP EIGRP neighbor. It only has a neighbor with the hub router. Show let's do a show IP route. It knows about it should know about the 192. It's directly connected. It knows about the 200 router, the 200 network, which came from router 3, and it knows about the 10.1.1 network, which came from router 1. Again, if we do a show crypto ISACEMP SA, it only has a tunnel open with the hub router. So here's how this works. If we're sitting on router 2 and we want to ping a host that sits behind router 3. So we're sitting on router 2 here. We're going to ping a host behind router 3 at 192.168.200.1. So ping 192.168.200.1. Okay, our ping request goes through. Let's do a trace route. Trace route 192.168.200.1. It goes one hop away. It goes from to 1.3, which is the tunnel interface that we assigned right down here to router 3. Remember, on this side, router 3 gets the 1.3 IP address, so it's one hop away. So now let's do a show crypto IPSec SA. We see now that it dynamically built this other IPsec tunnel. Well, this is phase 1, so this is the phase 1 negotiation, but we have a phase 1 tunnel between .5 and .9. So if we look at this back here again, .5 is the real IP for the WAN interface on router 2, and .9 is the real IP for the WAN interface on router 3. So it dynamically built that tunnel. If we do it, if you remember up here, we just did the same output. Oh, I thought we did. It must have been on the other. Oh, right here. When we did that previously, we only had a tunnel built to the hub router. But now that we needed to send traffic from router 3 to the networks between router 3 and router 2, it dynamically built that VPN tunnel for us so that we're only one logical hop away. So if we hop onto router 3, we should see that show IP IPsec SA, show crypto. IPsec SA. Now the reason I'm doing the IPsec, I mean, that's really only phase 1. To see the IPsec tunnel, we should be saying show crypto, CRYP, show crypto IPsec SA. That shows us the actual, IPsec tunnel where we see packets are being encrypted and decrypted. But the output's pretty messy. So here we see that it's going from .9, which is router 3's WAN interface, to .1, and we tab down a little bit, and here's our second interface that goes from 9 to 5, which is router 3 to router 2. And we can see the packets are encrypted and decrypted, etc. The reason I'm using the SA, the IPsec SA, is because it shows the tunnels up, and it's a much quicker and easier to look at output. It does not show us, however, like we see with IPsec, where we see that the packets are actually being encrypted by our IPsec policy. So I mean, there is a big difference. I'm just using this as a shortcut to verify tunnels. Okay, so now if we do a show IP EIGRP neighbor, we still only have the one neighbor back at the hub router. So even though router 2 and router 3 are receiving the routes from each other, it's using a hub and spoke configuration based very much on our frame relay. So router 2 is advertising its client network through EIGRP. Its neighbor is the hub router, router 1, on that tunnel 0. We disabled split horizon, so router 1 receives that update from router 2 on the tunnel, and it turns around and sends it out to the other multicast clients on that multicast or that multi-point GRE tunnel. So it comes into router 1 updates the routing table, and then lets router 2 and router 4 and router 5 know about that. So those are the basics for setting up basic DMVPN. So now I'll tell you the few things that have me concerned about DMVPN now that I've played with it. And let me preface this by saying, I have not been working with DMVPN for long at all. I just started looking into it. So I suspect a lot of the questions and the concerns that I have can be answered fairly easily once I get time to do a little bit more research into it. But here's the main two main things that I'm concerned about with DMVPN, at least in this configuration. Router 2 needs to get to a network in router 3. It doesn't know how to get there. I mean, it has to use the next hop, the NHRP protocol. It queries the hub, says, hey hub router, I need to get to this network. What's my next hop going to be? Router 1 tells it to use its next hop of 1.3, It builds this dynamic tunnel because they've all been configured with the same IPSec and IPSec policies. It dynamically builds this tunnel, sends the information, and then after 2 minutes of inactivity, that tunnel is torn down. Also, as far as EIGRP updates go, when this router has an update, it sends the update to the hub. The hub turns around and sends it back out to everybody else. So as you can see, this hub router is extremely important. These two devices, even though they're only one logical hop away through the GRE tunnels, they are not EIGRP neighbors. They are only neighbors with the hub router. So router 2 is not sending its updates directly to router 3 or router 3 sending them directly to router 2 or 4 or 5. They are all going through router 1. Likewise, when these two devices that we've configured need to communicate with each other, they don't know how to do it without going to router 1 first and asking router 1 to tell them what the next hop IP address is. And it comes back, and then once router 2 knows that, then it can build this tunnel, facilitate building this tunnel. Router 1 isn't used for the data transfer between router 2 and router 3. Once the tunnel's built, they'll send information through the internet directly to each other. But router 1 has to be consulted for building the tunnels and also for the dynamic routing protocol updates. So, and as a demonstration of that, let's do this. I think I've talked long enough. Let's see if router 2, if we start to see some timeouts on her. Okay, so there you see it. We went for 2 minutes and this tunnel disappeared. 2 minutes went by, or 120 seconds, that tunnel was tore down. So that's part of the dynamic, multi of the VPN solution, multi-point VPN solution. It dynamically builds and rips down those tunnels. So I have 3 concerns with it. Number 1, the spoke routers are not direct neighbors to each other for your dynamic routing protocol. I'm guessing with a little bit of looking and researching, I can find out if there's a way to make these EIGRP neighbors, or maybe you don't want to. My bigger concern is the fact that everything relies on router 1. If you lose your hub router or your hub site loses its connectivity to the internet, these spoke sites do not know how to communicate to each other. So let's give an example of that. So let's go into router 2. Let's do a quick ping test. Ping 192.168.200.1. Okay, so router 2 can ping the loopback on router 3 here. It's in the EIGRP routing table. Okay, so it's in the routing table. It's learned it through the tunnel interface, through the dynamic VPN, through that IP address. We're good to go. Now, let's go to router 1 and simulate a failure. What we're going to do is on interface fast00, which is what connects router 1 to the internet, we're going to shut it down. We're going to simulate a failure of router 1 or router 1's ISP or what have you. Okay, so router 1 went down. The state went to down. We started seeing our neighbors drop. Okay, let's go back to router 2 and do the same ping command. We lose it. Router 2 cannot reach router 1, doesn't have the information in its routing table, and can't reach router 1 to even ask router 1 how to build the tunnel between router 2 and router 3. Now, the redundancy aspect of it concerns me. My guess is, and I haven't had time to do any research on this, my guess is you can set up multiple hub sites. So maybe this is our primary hub site, and then we can configure R5 or R4 or some other site as a backup, or maybe active hub site. So router 2 might try to contact this site. If it can't reach it, it goes to router 5 instead. I'm just guessing on that. I haven't had a chance to do any verification on it at all. I can't see where you would ever deploy this in a larger scale environment, given the fact that you have such a Achilles heel here, if you will. If you lose this connectivity, your entire network goes down. So think of it. You're doing a change on this router or this link in a maintenance window, perhaps, but you're not just affecting the data center site or the data center site connectivity to the internet. When you do that, you affect, when you take this down or make this unavailable, router 2 can't get to router 4, can't get to router 3, can't get to office at router 5. You're basically taking your whole network down when you make those changes. So I gotta believe there is a way to do a redundant DMVPN hub configuration. I guess the other big concern, or not so big concern, but the other concern I do have about this is, again, say router 2 can't get to the resources on router 3 and you're troubleshooting it. If you hop in there and you start looking at your routing protocols and you're not familiar with the site and you don't see these routes being advertised in EIGRP, it could be difficult to troubleshoot, or it could throw your troubleshooting off. You need to make sure that like a network map like this is insufficient for this case. You need to specify that there are tunnel interfaces in here, and you need some text description of how your DMVPN is set up and configured. Coming in cold and trying to troubleshoot an issue with DMVPN could be a bit tricky. Whereas if you had point-to-point multiple tunnel interfaces to each site, I would think the troubleshooting might be a little bit easier. Plus, you'd reduce the fact that router 2 and router 3 could be direct EIGRP neighbors and update each other as to their routes without having to go through router 1. Also, if you lost your hub site, these other 4 or 5 or 6 or spoke sites, they wouldn't be cut off completely. Yeah, they couldn't reach your hub site, which is maybe where your Exchange server is and your other data center services are, but they'd all be able to get to the internet and they'd all be able to get to each other if that's needed. So again, I have a lot of research to do on DMVPN. I suspect a lot of the concerns that I have been addressed and can be addressed fairly easily. I just haven't had time to look into it at all yet. But if I do and I find out some good information, I will do a part 2 follow-up to this video and explain what I found out about how you can take care of some of the redundancy issues that are present here in a default DMVPN configuration. So I hope this was helpful to you, and if you do know any of the answers to my DMVPN questions, please leave a comment on YouTube and let me know what the answer is, or point me to the resources to find that out. I'd really appreciate it. Take care.